This is a quick video over average molecular weight of polymers. And what we'll see with this video is there's actually multiple ways of getting the average molecular weight, and they mean multiple things. I tend to think of these different methods of getting the average as pseudo averages. They're still very useful, but I tend not to think of them as true averages, and we'll see why in a moment. So let's just get started, and we're going to use cubes and apply the ideas we get from the cubes to the polymers. So let's start off by just finding the number average length of these cubes. So we want to find the average length of these cubes by the number method. So what we'll do is we sum up all the cubes that are Ni and multiply by the length I and divide it by the number of total cubes. So this one, there are 100 cubes that are one length long. There are 8 cubes here that are 4 lengths long, and then there is one cube here that is 100 lengths long. So therefore, if we just sum up all the top, that's 232 lengths, and then there's 109 cubes. So I believe that is 2.12. Let me check that real quick. Yeah. And you can see I already did this sort of. So there we go, 2.12. So that's the average length. Next, well, really that's the idea. So most people would say the average length is 2.2. So we call that the number method. And we're going to apply that to the polymers by doing this. We want to find their average molecular weight by the number method, and usually you'll see it as Mn with a bar on top is equal to the summation of Ni, the number of polymers that have Mi molecular weights, all divided by just the number of polymers. And again, that is the number average molecular weight. I think that one's pretty straightforward. Next, let's base it off of the surface area. So let's find the average length based off of the surface area of one side. So that's just equal to the summation of Ni times the surface area. So the surface area of a cube is just length I squared. And then what we do is just divide it by the summation of the number of cubes. And then we have to get rid of the length squared, because if this was centimeters, we wouldn't get a length, we'd get a surface area. So we'll divide it by one length to get a length again. I'm saying length a little too much. So what do we do, or what do we get when we do that? Well, we just have 1 by 1 is just 1 centimeter squared. So we just multiply that. So we get 100 plus 4 by 4. So that's 16. So 8 times 16. 16. And now we have a big cube, and that is 1 times 100. 100 squared. 100 squared. And we divide that by Ni, and the summation of all those. And that's 232. 232. And I believe that's 44. So 100 plus 20, 128. 128 plus 10,000, and then 44.08. So that's equal to 44. 44. And again, if this was centimeters, the average length would be 2.12 centimeters. The average length would be 44 centimeters. So now if I asked you to paint the surface area of all these cubes, which one would you want? Would you want the numerical length average or the surface area length average? You would most likely want the surface length average if you're going to paint the surfaces of them. Because you're not going to be able to, if you just try to paint this one cube, you're going to run out of paint before you can get to any of these. So this is much more important when you're wanting to talk about the surface area. And this is just more important when you want to know the number one. And we can even go on to find the volume length average, which would just be the summation of the number of cubes that have length I cubed, all divided by the summation of Ni Li squared. And that would give us the volume length. So this would be important if you wanted to put these all in a giant box. And if all I gave you was the length average, which one would you want? Would you want the numerical average, the surface area average, or the volume length average? So if you're going to put them in a box, you would want the volume length average. If you were going to paint them, you would want the surface area average. And again, this surface area average, how we calculated it was just for one side. Just for one side. So that's why we have a 1 right there. So that's the general idea. And with polymers, the reason we have these different types of averages is because these polymers are much more important when you're dealing with viscosity. So how we do it is we say, okay, we're going to do the weighted average molecular weight. So that is just simply m bar w. And how we calculate that is it's identical to that. Instead of having L, we put mi. So we have the summation of the number of polymers that have the molecular weight mi divided by summation of ni mi. Whoops, that's squared. So this is the weighted average molecular weight. And that's important because when you're wanting to find maybe the viscosity, you would use this average. Now, the one thing I want to leave you with is when you compare the weighted average and the numerical average, you get this thing called Q, or the polydispersity index. And all that is I believe, mw bar divided by mn bar. And usually that's between 2 and 5. So there's actually a lot of other ways of calculating the average molecular weight of polymers, but these are two important methods, and the polydispersity index is also very important. So that was a quick video over how to calculate the different types of molecular weight averages for polymers.